FIMMPROP is a powerful tool by Photon Design for applying the rigorous EigenMode Expansion method to large PIC components. This allows you to simulate things like entire ring resonators all on a laptop in a couple of seconds. In this video, we're going to show off some common devices and show how we set up their computational regions. During this video, we're going to assume that the cross-section of your waveguide has been correctly optimized. There's another video on this already, but just in summary, I'm going to use you can use the plot section tool. If we just click in the middle, we can see the amplitude of the mode has gone to 0 and its gradient has gone to 0 before reaching the boundary conditions of our cross-section, both the left and right and up and down, the X and the Y. So I'm here with a Y splitter in FIMMPROP, and I'm going to add on what we call our path computational regions. Now, path computational regions follow the curve of any path you have defined, and I'm going to use a width here that, let's assume, is the correct width for keeping the mode not interacting with the boundary conditions. So I have a default width attached on here, and I'm just going to click onto all the paths. And you can see that path computational region follows the path that I've defined. Now, one point here, you can see that these path computational regions are intersecting. Now, a path computational region will not simulate coupling with another computational region, so we need a different computational region to join these two together. And this is where we can add what we call a span computational region, which does simulate coupling. Ooh. So let's just move these away to get some space and add in a span computational region. This attaches to one of the paths, and it has a positive length and a negative length, and it has its position along a path. And we want this to sit connected to this first path here. So I'm going to set the negative length to 0. And its position to 0 along the path. So this is now connected to this straight section here. Now, how big do we make this spanning computational region? Well, if you might remember from our setting up our computational region of our cross-section, at the edge of these path computational regions, the field has gone to 0. So the point after which they start intercepting, so if I drag these back, where they overlap, there are two non-zero fields, and therefore we need to simulate the coupling. So put simply, we need it such that the spanning computational region comes to the point where the path computational regions overlap. So let's just adjust the size for this now. And then I can simply drag these back to click on here. It's still overlapping a little, so let's just drag this further, and then this needs to be a bit wider too. So this would be the correct implementation of a spanning computational region. Next, let's look at this ring coupler. Now, I'm just simulating a quarter of the ring here. The reason you might do this is to use this quarter for a sub-device to be used to build a full ring resonator. But let's just take this as an example. First, let's add on our path computational regions. And once again, they overlap here. So I'm just going to follow the exact same rules and drag back these regions and add in the span computational region. You see that it doesn't connect to this path facet here until I set the one of the pos or negative lengths to 0. So the positive length set to 0, the S parameter, let's set that to 1. That means it's all the way along this path. And then let's add a little bit of an offset, something like 0.2. And let's see where we need to position this. So something like this would be acceptable. And just to showcase this would be a full ring resonator made from a similar device. So you see the comp region here, the spanning comp region for the coupling region, and then going into those separate path regions for the arms. Next I have here a racetrack resonator, similar to a ring resonator, but just has this extra straight section. So let's do the same procedure again. Add on our correct width computational regions. And I would like to position this somewhere in here to get some coupling, and where we have overlap we want to replace these with a spanning computational region. That's what we've set out so far. Now I see a problem here. So previously we set one of the positive or negative lengths of the spanning comp region to 0, such that it could attach to one of the sides, one of the path facets. So let's set that to 1. So that could attach to this path facet here, but it can't attach to two path facets at the same time. So the spanning computational region won't be appropriate here. However, there is a solution. What we'll do is we'll use a subpath. So this is my subpath button here, and I can drag on a subpath from here and add my waveguide back on. Now, when we use a subpath, this entire block is just considered as one path, rather than as two separate paths which need to have a span region. So we can actually simulate the coupling between these two paths just using a path computational region. So if I offset this a little, I can then attach on these sections here. You will also see there is some overlap here, this decoupling region between these two bent sections. So I'll just follow the exact same procedure as before and add on a spanning comp region. So add this here. I'll set the positive length to 0. I want it all the way along this path so that it connects here. And after playing around with the numbers a little, we can get to this. And this would be copied on the other side as well. We can see this applied in this pulley coupler example as well. I've once again used subpaths. So this section is a subpath of this section here. Let's make sure these are attached on. And once again, I can use the path regions wherever I can. I want to simulate the coupling between these two, remembering this section is a subpath of this section. And I show this example as well as that pulley coupler just to show that the computational regions on subpaths can be curved. Once again, investigating this spot here, I'll have to add in a spanning computational region for this decoupling area. Setting the negative length to 0, setting it to be at 0 along this path. That's a little bit offset. And then we just reattach on these paths. And the same will be true for the other side as well.